Hello, Mr. Cody.
Good morning.
I'm so glad to be back home today. I'd like to be on campus with you, but at least I'm in my own house, and that's good. All right. I know 2 people aren't going to be here, and that would make 6, and Ethan would make 7. And I think that's all we have. So Ethan will probably be here in just a minute. But I thought about skipping what we're going to do today, the definition of the limit, but it's just so fun when you understand it. I'm not going to say if you understand it, because you are going to understand it. I'm going to help you. But when you understand it, it's one of those things that you go back to and read a year from now and say, I can't believe that made sense. I can't believe I know what that's even talking about. So before we start the definition of the limit that's in the notes, the back of the page that we were writing on yesterday has these 2 applications. And I don't have time to read both of them to you. I want to talk about this application 2, and then I definitely want you to go back and read application 1. These are 2 things that I'm really, really proud of, because it's difficult to explain the definition. I could read the definition just to freak you out if I wanted to, but I'm not going to freak you out. I'm going to explain it first, and then we're going to look at how this explanation applies to that definition of the limit. All right, and let me preface this by saying I don't know anything about target shooting. I made all this up. It sounds reasonable to me, but somebody who's really been in shooting competitions may go, that's not how it works at all. So complete fiction here. In my made up, extremely simplified shooting competition, there are different size targets, but they all have the exact center labeled L. And L is surrounded by a circle of radius. Let me give you 2 words right here. This symbol is the Greek symbol epsilon. This symbol is the Greek letter delta. And those are both in the definition of the limit, or we would use something simpler than that. All right, this is telling us that the target has a radius of epsilon units. So somebody at the competition sets that epsilon. It could be a little bitty circle or a big circle for beginners, but somewhere, this is the point that I'm trying to hit right here, this L. And I know that hitting anywhere within, and I may go back sometime and make that a white circle instead of black, because it doesn't show up when you write on it. But if I hit anywhere within that radius of epsilon, I still win the competition, get the points, whatever. Epsilon's the radius of that circle. And again, the shooting competition officials can make that epsilon as small as they want it. You get points for hitting the target anywhere in the black circle. Ideally, if you could hold the rifle horizontally a distance of exactly 3 feet above the ground. If this were always, no wind, no trembles, nothing, 3 feet above the ground, then you would hit L, the bullseye, exactly. But because of different, let's see. Because of different shooters' height and steadiness, it's very hard to hold that level with no wiggling at all. So let's say that this shooter, instead of being exactly 3 feet above the ground, he or she deviates from that the tiniest bit. Then let's call this X, the amount of deviation, the actual, not the amount of deviation, but the actual height. So that shouldn't be X. X is the actual height. So if I want to find the amount that this perfect trajectory deviates from, or the amount that this shooter's trajectory differs from the ideal trajectory. The ideal trajectory is 3 feet above the ground, but I want to know how far off this dude is, dude or dudette. How do I find the difference between X and the ideal? Just think, when you say, how do you find a difference? Most people don't think math when they think the word difference, but how do you find a difference in math?
Subtract.
Yeah, you could either say this is 3 minus X or X minus 3. If he was a little bit high, you would probably say X minus 3 because X would be bigger than 3. If he's a little bit low, you'd probably say 3 minus X because X is a little bit lower to the ground than 3. Or to take care of both scenarios, above or below, you can just call this the absolute value of X minus 3. That takes care of X minus 3 or 3 minus X. You'll get a positive distance there no matter what. So absolute value of X minus 3 is this little amount of offness in the ideal trajectory. It's the deviation in muzzle elevation from the ideal position of 3 feet above the ground. All right, if I was in class right now, I would be looking to see if you were all nodding, but I can't, I only see, well, I don't see anybody's face. Y'all must all have bedhead this morning. Does that make sense so far? I need 4 quick yeses or a no. 1.
Yes.
2.
Yes.
3. Cody?
Yes.
Okie dokie. All right, that's absolute value of X minus 3. If P is the point of impact, it's really hard to write on this black, but I'm going to say P is the point of impact, then the absolute value of P minus L is the distance between the point of impact and the exact bullseye. All right, bullet's gonna be off by just a little bit. Absolute value of the difference between the bullet, where the bullet hits the target, and the ideal point where the bullet hits the target, that absolute value is the distance between the point of impact and the center of the target. All right. Now, I'm not going to wait on 4 yeses after every sentence, but if somebody's going, no, you lost me, just yell at me and I'll back up. The amount of deviation from the desired muzzle height of 3 feet is determined by the radius, epsilon. The more precise you have to be, the less shaking you can do over here. And since epsilon is the radius of that circle, the smaller epsilon is, the smaller absolute value of X minus 3 is going to have to be. The smaller the circle, the less the muzzle height can deviate from 3 feet. Let's call the acceptable amount of deviation delta. Delta is how much it's okay to be off and still hit inside that black circle. And so delta depends on epsilon. This amount of deviation depends on how big the black circle is. The smaller the black circle is, the smaller the acceptable amount of deviation is. And that's exactly what acceptable deviation is, how much it's okay for your trajectory to be above or below this ideal trajectory. Based on the shooter's distance from the target, and I'm sure a lot of other factors, someone determined that for the bullet to hit the target within epsilon units of L, That just means within the black circle. There must be no more than epsilon divided by 4, or a quarter of that distance in, sorry, didn't have that at the hospital. Whatever the radius of this target is, somebody has calculated that delta, the amount of offness, has to be only a quarter of whatever the acceptable amount of offness is here. So delta has to be a quarter of the radius of that circle in order for the bullet to hit within that circle. For example, if the radius of the black circle is 4 inches, then the muzzle can only, don't tell me, the radius is black. Where did I get a 4th? Delta is, that's supposed to be 1. Yeah, I just made this last year, so I just found a typo. If epsilon is 4, then delta, the distance between ideal and actual trajectory, has to be within an inch. If this is 4 inches, this trajectory can only vary by 1 inch of the perfect 3 feet off the ground when the trigger is pulled. All right, I am going to stop for 4 yes, 4 okays, or a now.
Okay.
1 okay,
Got it.
Yeah,
Two.
got it.
3. Miss Jacqueline?
Yeah, I'm good.
Okay. Whew, I'm proud of this story. It's better than any story I ever made up for my kids. I'm not that creative. In general, for any epsilon greater than 0, and it really doesn't make sense that you'd have a target with a 0 radius or a target with a negative radius. So that seems kind of pointless, but in general, for any epsilon greater than 0, and again, epsilon is the deviation of the bullet from exact bullseye. There is a corresponding delta, and again, delta is the acceptable amount of deviation in the muzzle elevation, such that as long as this distance is within that acceptable range, then your bullet will be within the acceptable range from the bullseye. And if you understand that, the definition of a limit is going to make a whole lot more sense, and you're going to be so proud of yourself. So the definition of the limit was on the first page of the notes, and I used to not tell that story because I just made it up last semester or last year. I used to just read this statement and watch people's eyes bug out. I'm kinder than that now. Let f be a function. Here's a function defined on an open interval containing c. There's some function to the left of c, there's some function to the right at c, but it may possibly be, there may possibly be a hole in the graph at c itself. And that's okay, because we know that limits still can exist even where there's a hole in the graph, because we're just going to get close to that c. We don't have to necessarily be able to actually let x be c. All right, let f be defined in an open interval containing c except for possibly at c, and let L be the bullseye. L is what we want the function value to be at c. Then the absolute value of x minus c, that's the distance between x. There's an x here somewhere. There's an ideal level of trajectory for that gun, and for any x, this distance is absolute value of x minus c. So as long as that distance is less than some delta, and in the other problem, delta turned out to be a fourth of the epsilon. We're going to learn how to find the delta in just a minute. But as long as that absolute value of x minus c is less than delta, then your function value f of x will be within epsilon units of L. All right, you're probably going, shooting made more sense. Let's look at the graph and compare it to that target picture we had. Here's some function, f of x. It's defined around c, but maybe not at c itself. The definition of a limit says no matter, what did I use? What color did I use here? I want it to be the same color. No matter how small of an epsilon you give me, and again, that's the radius of the circle in our target, no matter how close you have to tell me I have to get to that function value being L, I can get that close by choosing an x that's sufficiently close to c, an x that is within delta units of c. Now, the rest of this inequality, 0 is less than absolute value of x minus c, because the function's not or may not be defined at c, then that distance, I better not let that distance be 0, because I can't let x be exactly c. As long as that distance is bigger than 0 and less than delta, then I'm gonna get some points. My f of x is gonna be within epsilon units of L. All right, you're gonna have to read this several times tonight and keep flipping it back over, or put these two side by side and go, oh, the L is the bullseye, the epsilon is how close I have to get to the bullseye, the x is let's say the c in this case would be 3, and the absolute value of x minus 3 is an amount of offness, the distance between x and ideal. So this is the distance between x and the ideal value of c. For any epsilon in the whole wide world, no matter how small you make the target, there is a delta such that if the distance between x and c, that's the absolute value of x minus c, if that distance is less than delta, then the distance between the function value and the target, that would be like the point and bullseye in the other example, that distance will be less than epsilon. And then I say this about 10 different times because that's how many times it takes to even come close to getting it. This definition means if you give me an epsilon, no matter how small, I can get the function value to be that close to the bullseye by finding how close x has to get close to c. The smaller an epsilon you choose, the smaller delta I'm going to have to choose. The smaller the bullseye, the less variation I can have between that perfect trajectory and the path of my bullet. As a matter of fact, I can get f of x infinitely close to L by letting X be infinitely close to C. And that's what this notation means. This means for any, no, I don't want to say it that way. This means I can get the function value to be infinitely close to L by letting my X get appropriately close to C. And I have to figure out what that appropriate is. Now, again, with this, some official figured out that for any radius you give me, this amount of deviation could be a quarter of that. If I had a target with a 12-foot bullseye, then this trajectory could be off by 3 feet. I could lay the gun on the ground and still hit the bullseye if you gave me a bullseye that big. But the definition of a limit is no matter how small of a bullseye you give me, I can find how much wiggle room I have here in the path of my bullet. All right, because delta depends on epsilon, that means how close you need to get to C depends on how close you want f of x to get to L. You must choose an appropriate delta as some expression involving epsilon. Now, shooting official figured out for this problem, delta needed to be a quarter of epsilon. I'm going to show you how to find delta for any function. To do this, start with absolute value of f of x minus L and work on it until it becomes absolute value of x minus C. And then you work backwards. Once you find your appropriate delta, you work backwards to actually do the proof. That's what we're going to do today, is proofs of limits. And we also need to start 2.2, but we don't have to finish it today. So just like trigonometric proofs and pre-cal, proofs are the only thing where I'm going to grade you on form and style. I'm going to say, nope, that's not a proper proof if you don't do it just the way that I'm telling you to. And this first one I typed out completely for you so that you could just listen. And I have the steps that you need to follow in each proof that you do. I think you have about 4 proofs tonight in the homework. All right. The problems in tonight's homework, the directions say something else in the book. When I say I want you to do these 4 problems, just like we did in class, I mean, don't follow the directions in the book. Do a proof just like we're fixing to do. And you must find the limit first. Well, this says find the limit as x goes to -3 of the function 2x plus 5. 2x plus 5 is your f of x, and -3 is your c. Now, I know 2x plus 5 is just a line, and if I want the function value at -3, I can just put -3 in the place of x, and I'd get -1. So when I say you have to find the limit first, I can tell by substitution that limit is 1, or -1. All right. Your first thing I'm going to grade you on in the proof is you have to write the definition of a limit so that you show your goal. This is what I'm trying to prove. Every proof starts with a show that. So here's the definition of the limit. For show that, let me let people know their puppy's on video. Hey, hey, woo-hoo! Garrett, can y'all corral the dogs for another 30 minutes? I'm teaching. Okay. Okay, here's the definition. and you just write this 3 or 4 times and you have it memorized. Show that for any epsilon greater than 0. Epsilon was the radius of that circle I had to hit. For any epsilon greater than 0, there exists a delta greater than 0, such that if the absolute value between x and -3, the absolute or the distance between x and -3 is actually x minus -3, and x minus -3 is just x plus 3. So this is the distance between x and -3. If that distance is less than delta, then the distance between f of x and -1, again, the distance between f of x and -1 is f of x minus -1, and I just wrote that as f of x plus 1. We're trying to show that if this is true, then this is true. Well, the first thing we have to do is start with this and find that perfect delta. See how this relates to that. All right, at first you're just kind of copying stuff down. You just go, okay, she said, I don't know why, she said to start with f absolute value of f of x minus L is less than epsilon. So here's my f of x minus -1. And the only reason that's plus 1 is because the difference between f of x and -1 is f of x minus -1. We're going to say if that has to be less than epsilon, then I can combine like terms and say that'll have to be less than epsilon. I can factor out a 2 and say, well, that'll have to be less than epsilon. I can divide both sides by 2 and say, well, then that'll have to be less than 1/2 of epsilon. Whatever epsilon you give me, this distance is going to have to be less than 1/2 of that. So that's how I find my delta. In the target practice problem, some official gave me the delta because I didn't know calculus yet. But now I know if I start with f of x minus L and change it into this other expression, and it always works, you always can get that other expression out of it, then I find what fraction of epsilon delta has to be. All right, that's the step of finding delta. The last step is actually your proof. You have to find the delta before you can do your proof. And anytime you start or anytime you do a proof, you have to state your hypothesis. The hypothesis is straight out of the definition. The definition says for any epsilon, or if for any epsilon greater than 0, there exists a delta greater than 0, such that if the absolute value of x minus c is less than delta, that's your hypothesis right here. And all I've done here is put -3 in the place of c. So absolute value of x minus -3 is just x plus 3. And then the cool part about finishing this is you basically, once you find your delta, your proof is just working back up. You're starting with this, you want to end up with that. So we go, okay, well, we decided delta is going to have to be epsilon over 2. And I can multiply both sides by 2. And I can distribute that 2. And then, because I know what I want, because I know that I want that to be f of x minus L, I just split that 6 into what I want it to be. And then you always end a proof with your favorite expletive, favorite PG rated expletive. When you write the proofs in the homework and on the test, I want your steps numbered. And if this was worth 6 points, you would probably get 2 points for each part of this. You get 2 steps for saying, I know what the definition of the limit is. You get 2 points for saying, I know how to find the appropriate delta. And you have 2 points for starting with your hypothesis and ending up with the conclusion that you stated up here. All right, dare I ask for 4 okays again?
Okay.
That's what I expected. Okay, maybe. Well, that's all right. I accept that. Julia, Jacqueline?
I'm good.
Okay.
Yeah, I'm good, babe.
Yeah, you can sound a little unsure. You've only seen one of these. Let's give one geometric interpretation of what we've actually proven. And then I think we're only going to have time to do one of the 2 examples at the bottom of the page. But I think if you have this one typed out and we work through another one together, I think you'll be okay for doing those 4 proofs at the bottom of the homework. How are we doing on time? Yikes. Okay. So here, the geometric interpretation of what we've just found. F of x equals 2x plus 5 is this line. And we have found that to be within some tiny amount of that function value to -1. If we want to be some tiny amount, let me start that sentence again. If we want the distance between f of x and -1 to be less than some tiny amount, then we have to be within half of that distance of -3. If we want f of x to be within a half a unit of -1, a half a unit of -1 is from -1.5 to a half. If I want the function value to be between -1.5 and -0.5, then my x has to be within half of that distance of -3. Well, half of that distance would be a quarter. If E is 50 cents here, half of that would be a quarter. And a quarter unit of -3 is -3.25 to -2.75. And you can tell from your XY chart, this is bullseye. I know that when I let x be -3 in this function, I get y is -1. But in another function that I couldn't actually let x be -3, say there's a hole in the graph at -3, I can still show that I can make y be within a half a unit of -1 by letting x be within a quarter unit of -3. Or I can get y to be within 1 unit of -1. 1 unit of -1 is from 0 to -2. I can let y, or get y to be within 1 unit of -1 by making x be within a half a unit of -3. All right, we're going to do one more proof, and then I have the beginning of 2.3 is so easy that I can do it very quickly. So I'm not quite worried about running out of time yet. You definitely need to see one more proof, and I'm going to write it just like it has to be in the homework and on the test. And that is number 1. You have to show that you know the definition of the limit. You have to write it as a complete sentence. Show that for every epsilon greater than 0. No matter how tiny, you can make a tiny little bullseye. For any bullseye size you give me, there is some corresponding amount, some delta, such that if, and you need your hypothesis and your conclusion, your hypothesis is if the distance between X and C, as long as that distance is between 0 and delta, then the distance between f of x and L, that's the distance between f of x and L, that distance will be less than any tiny little epsilon you could give me. Now, the only other thing that, are y'all through? Is anybody still writing that? Okay. The only thing that you may want to add to step 1 is actually putting this value x is approaching in for C, putting the function value in for f of x, and oh, we got to find the limit before we know what to put in for L. So I can find this limit by letting x be 2. 3 times 2 is 6. 6 minus 2 is 4. So I'm going to say, I'll just use brackets for that. I'll just say this with all the numbers plugged in the right place would be if 0 is less than the absolute value of x minus what goes in place of C.
2.
Yeah, that's the number x is approaching. This is what I'm saying the limit is. So if the absolute value of x minus 2 is less than delta, then absolute value of, what do I put in place of f of x?
3x minus 2.
The function. And you may want to use parentheses just so you can see that's your f of x. Certainly mathematically they don't make a difference, but f of x minus L, that's the whole thing we're trying to prove. So that's step 1. Step 2, what is step 2 at the top of the page? What does that say?
Find an appropriate delta.
All right, and out to the side, it shows how to find that appropriate delta. Start with your f of x minus L and work on it until it becomes absolute value of x minus C, and it always will. So start with absolute value of f of x minus L, and actually, I need to just take, since we're not going to have time to do this one, I'm going to do the rest of these steps here. So we're going to start with absolute value of 3x minus 2 minus 4 is less than epsilon. And I'm hoping somehow I can clean that up and it'll just become absolute value of x minus 2. Well, I can almost see how that will happen. I'll combine like terms, and then I'll factor out a 3. And then I'll divide both sides by 3. And I figured out what delta has to be in order to be able to hit the bullseye or to be within epsilon units of the bullseye. Delta just needs to be 1/3 of whatever epsilon is. And then step 3 is actually doing the proof. Show that your original claim is true. Start with the hypothesis and then really just work backwards till you get the conclusion that you wanted. You'll always get that conclusion because you chose the right delta. So start with the hypothesis, and the hypothesis is if, this is the hypothesis right here, if 0 is less than absolute value of x minus 2 is less than delta, then what have we chosen our delta to be? What if we said delta is equal to?
Epsilon over 3.
Good. Good speaking Greek there.
Thank you.
We've got to turn this into that. Well, this gives us the pathway for doing it. If we multiplied both sides by 3, and then we distributed that 3, and I only know what to do next because I know what my goal is. I want to end up with this, so that tells me how to split the 6. Without that, I wouldn't know whether to call that -6, -8 plus 2, or -3 minus 3, but I know what I want to end up with, so that's how I'll split the 6. I have proven that the limit of this function as x gets close to 2 is 4. The function may have a hole in the graph at 2. I don't know. Well, I do know this particular function doesn't have a hole in the graph at 2 because it's just a line. But I can get this function to be within any tiny amount of 4 that you want by getting x to be within 1/3 of that amount to 2. And even if you're still a little shaky, if you're like, I might have gotten that, not sure, tonight, I would suggest that you read back over this and understand the symbols in it. And then you read this and it uses the same symbols. By the time you've looked back over these, when you go back to the definition of the limit, you'll be saying, oh, that kind of makes sense in a sick way. And by the time you've done 3 or 4 of them, you'll just be rattling it off like a calculus grad student. All right, so we are, let's see, how much time? We have 10 minutes to talk about 2.3. We'll just see how far we get. But the homework tonight, definitely these 4, just like we did in class. If I don't see number 1, number 2, number 3, then it's not right. And those that have a blank, you have to find the limit before you can do the proof. Any questions? All right. It's about time we do something easy after that. In 2.2, we talked about two different ways of finding limits. We found limits graphically by putting our fingers on the graph left and right of whatever x was supposed to be approaching and moving them in on the graph until we could see what y would be close to that given x value. So we found limits graphically, and then we found limits numerically by making an XY chart. You could see as my x's get close to something, my y's get close to L, whatever it is. Well, those tables are kind of a pain in the chart, or a pain in the neck, and even graphing, sometimes it's hard to see what the limit is, especially on a graphing calculator, because when there's a missing pixel that represents a hole in the graph, it's hard to see that. So the primary way we're going to find limits is analytically. And for a lot of basic functions like linear functions, if you want to know what the limit of this was, because we knew 2x plus 5 is a line that doesn't have any holes in it, we just let x be -3 to find that limit. That's called direct substitution. And direct substitution is a fine way to find a limit as long as it works. As long as you can do direct substitution, that's the easiest way to find the limit. Let's see if these three rules make sense. If the first one says the limit as x approaches c of some number b, f of x is just a constant function. F of x is b here. So any, miny, miny, mo, let's say we had the function f of x equals 3. Then what would y be approaching no matter where you are on the graph? No matter where you are on the graph, the y's are all did anybody answer that? What are all of my y's no matter what x I'm looking at?
3.
They're 3. So the limit of a constant function, no matter what x is approaching, the limit of a constant function is just the constant. All right, what about the limit of here? This is just the identity function, y of x, y equals x. Y equals x is that line that bisects the first and third quadrants. So if you want to know what y is as x gets approached, as x gets some, all right, one more time. If you want to know what y is getting close to on the line y equals x, well, if y equals x, then whatever x is getting close to, y is getting close to the same thing. If you had the limit as x approaches -4 of x, well, on this line, if x was -4, y would be -4 also. And then this one is x to some power. If you just have x to some power, that's a continuous function. That's, you know, it either looks like x squared or -x squared or x cubed or -x cubed. It doesn't have any holes in it. Just evaluate it by direct substitution. Just put 2 in place of the x and you'll find the limit. Now this 6 through 36 even, I think that's where we can get to and stop. And there's one piece of paper that I should have out that I don't. And my wireless mouse. Oh, there it is. This is on page 91 of the book. I do happen to have the book open. Page 91. What did I say? 6 through 36. All of these 5 through 18, you can find the limit by direct substitution. On number 6, just let x be 9. On number 8, just let x be 1. Number 14 can be evaluated by direct substitution because you can let x be -5. Now, if that said find the limit as x goes to -3, could I let x be -3 in that function?
No.
No, I just couldn't do that by direct substitution. But all of these first 5 through 18, the limit can be evaluated by direct substitution. So that's the easiest problems you'll have in calculus. And then, how are we? We got 4 minutes. You do 5 through 17, and then you skip to 23. You can do these by direct substitution. 24, you can let x be pi. You can tell me what tangent of pi is. And number 26, let x be 2. And you would have sine of pi over 6. You can do that. And you can do that. And you can do that. So all the way up to number 29 can be done by direct substitution. And then, all of those can. Yay, we got to a good stopping point up until number 35. So here's the homework, and all of the ones in 2.3 that I'm going to give you, you can evaluate by direct substitution. We'll pick up tomorrow. What do you do when you can't do direct substitution? So the homework, the only thing on this page, we didn't get to talk about these. What do you do when you can't use direct substitution? So the homework, is these and those. And I'm probably going to take it up tomorrow because I want to see your delta epsilon proof to make sure that you're doing them correctly and you'll get that right on the test. Don't worry about these tonight. We'll get them tomorrow. Any questions? All right. Y'all work on making those proofs make sense. And have a great day. See you tomorrow.
You too.
Probably on campus.
You too. Have a good day.
Thank you. Miss Julia, you okay? Miss Julia?